Welcome to a lesson with Dr. Powell. Let's talk about why, for a symmetric matrix, one that's equal to its transpose, with all real entries in it, why are all of its eigenvalues real? All of its eigenvalues will be real. Um, we look at the characteristic polynomial, we look at all the roots. They're always going to be real for a symmetric matrix. That is, why is that? Why are all the roots real? Well, we're going to use an idea here. Let's define the complex conjugate of a complex number to simply just be changing the sign of the imaginary part. Okay, and then we also have that if you multiply a complex number by its conjugate, the difference of two squares, so a squared minus bi times negative bi, but with the I squared, that's another negative, so it becomes a plus b squared. So it's really just, if you thought of like ab as a vector, it's really just the length of the vector squared. It's going to be a positive number, a positive real number even. So given any, so in general, so given any complex number w, you multiply it by its conjugate, you're going to get a real number that's going to be positive. Assuming that w, of course, is not zero, then you'll have this condition right here. So we'll use that idea as we move along. All right. So let's suppose that there is an eigenvalue. Just take any eigenvalue, lambda, or matrix A. It has a vector v associated with it, so that AV is equal to lambda v. Okay. Now, now in this case, I guess if this is going to be true, I mean, it could very well be that we'll have to bump up things a little bit and think of our, what if we had entries in our vectors? So A has all real entries, but maybe V comes from Cn, meaning instead of Rn, like maybe there's some complex entries in V in order to make this work appropriately. Okay, so maybe we're actually working in here. However, our matrix A in real numbers also acts on this vector space right here because real numbers are also complex numbers, just with imaginary part 0. Okay, so just kind of keeping that in mind, what we're going to do is we're going to think of AV as being a vector. We take its complex conjugate, meaning we take the complex conjugates of all its entries. And we dot it with AV. So all the entries of this vector AV, we're going to take the complex conjugates of all those and then with the dot product, we're multiplying respective pieces, and it's going to be the same thing as this going on in each component. So I have a vector then what we do is we add all those up in the dot product, and we end up getting a number. That number is going to be greater than 0. So we're going to keep that in mind as we're heading along. Okay, now we can compute. Let's think about this in two different ways. All right, first of all, A is all reals anyway, so we can just think of think about this, right? And to make this matrix product work, we go transpose. And then we have, let's see, so we're going to take the transpose of that, which is the same thing as A transpose A, B, and that transpose. Now, notice that this part right here is just A squared because A is symmetric. Okay, squared. So in this calculation, what do we have? So this is going to simply be V lambda. So this is going to be V lambda. Now we're doing A twice, and the scalar is going to pass through each time. So this is like A times AV, and AV is like lambda V. The lambda can come out again, and A applied to V again gives us another lambda. So we're going to get it. So we're going to get lambda squared v, which is going to be the same thing as lambda squared v. Okay, so that's what this dot product is equal to. But on the flip side, we also can look at it this way. We can also look at it this way. So AV, right, like this, is equal to lambda V with the complex conjugate of it, right? Complex conjugate here, complex conjugate there. So why don't we look at it that way as well? So so this would be the same thing as lambda V complex conjugate dot product with lambda V, all right? So you can think like that if you wanted to. Complex conjugate of lambda here, complex conjugate of V. So we're just taking the complex conjugate of each entry, and in particular, you can, if you have two complex entries, what we're using this idea that AB conjugate, well, we're already using AB for other things, but if you have like KR conjugate is actually equal to K conjugate R conjugate. So we're using that idea that it splits there in general, so cross entries and whatever else. But using that idea, we see that this is, so we have lambda, and we can rearrange because these are the scalars. And then what we have is we have, and of course, realize that this was a transpose. Okay, that's a transpose. Keep that as a transpose. This is V. Okay, that V. Okay, so notice that these two things are equal. That means that lambda squared is equal to that. Of course, you can divide both sides by lambda, and we end up getting lambda is equal to lambda conjugate, which is the same thing as, so if it's equal to its own conjugate, that means that the imaginary part had to be 0, so it had to be real. So lambda is real. Now, if you'd like to see, for instance, that this little property is true, you can always experiment with it, but it works out rather nicely in general. Right here, if we did like A plus BI times C plus DI, and if we just change the pluses to minuses, what's the difference? Well, notice that when we get A times C and then this part times this part, the negatives cancel out. So it really doesn't change anything but like the outside and the inside. But changing out, but the outside and the inside is exactly the part that gives us the imaginary thing. So, I mean, you can work that out, but actually, this is a nice property right here, which was implicitly used in our argument down here. But nonetheless, we have just remembering what we did. We took a symmetric matrix A, and then we showed that all of its, or any eigenvalue of it has to be a real number. So all the roots of its characteristic polynomial have to be real. Thanks for watching.